Well, good morning or good afternoon or good evening, depending on where you are in the world. And welcome to today's Aviation Week webinar. Aerospace leaders discuss advancements in additive and a DfAM, that's designed for additive manufacturing, less future. It's sponsored by Velo3D. I'm Ed Hazelwood, and I will be moderating today's event. We have just a few announcements before we begin. This webinar is designed to be interactive, so there's a dock of widgets at the bottom of your screen, and it will allow you to learn more details about today's speakers, to download resources, and to participate in the Q&A session that takes place during our presentation. The slides will advance automatically throughout the event, and you may also download a copy of the slides via the resources widget. Toward the end of our webinar, we're going to ask you to complete our survey. It's found on the right-hand side of your screen. And please take a minute to fill this out before you leave us today, because your feedback gives us valuable information so that we can improve future events. And lastly, if you experience any technical problems, please click on the Help widget at the bottom of your screen, or you can type your issue up in the Q&A area, and we'll be glad to offer you one-on-one assistance. Now, on to the presentation. Aerospace leaders discuss advancements in additive and a DfAM-Less future. Discussing today's topics are Daniel Dombrowski. He is a mechanical engineer at FAA FTT Kratos. TK Kallenbach, I'm told he's the legend. He's also the Chief Executive Officer and Independent Aerospace Consultant for Thales In-Flight Experience. And Will Hastings, the Director of Solutions Engineering at Velo3D. To learn more about our prestigious panel of speakers, please be sure to check out their impressive bios in the speaker bio widget found within the webinar platform. So gentlemen, let's get started with this discussion today. Let's start broadly. So basically, Will, I'm going to go to you first. What's happening in the metal additive space within manufacturing broadly?
Yeah, thanks for that, Ed. So one of the key things we're seeing right now across the market is, first off, larger machines. That means larger parts. So that's more applications that can be printed. Examples of this is now it's feasible to print entire jet engine combustors for smaller size engines. That was not possible with the older systems out there on the market. And then additionally, we're seeing this move from company-specific material specifications to broad-based industry specifications such as AMS. And then finally, the standardization across the industry is helping to push from vertically integrated companies printing parts to using contract manufacturing and using the industrial base similar to CNC and other technologies.
Okay, Daniel, you want to expand, take that issue as well and give us your perspective?
Sure. Where I've seen additive manufacturing and metal transitioning is, when it first came on the scene, a lot of it was, it was for lack of a better term, trinket type stuff, fixture rigs, look what we can do type things. And then it went from that to, real parts in prototypes. I do a lot of prototypes with Kratos, and that's sort of, the sandbox that I'm in. You see a lot of additive working their way into prototype rigs, where we're not talking, small stuff. We're talking bigger test fixtures, and then eventually, you're also seeing additive parts start working their way into real flight engines, and that's been the last couple of years taking that leap into being real parts. So that's where I've seen it. It continues to build trust, and as there's more experience with additive, people tend to allow it into more programs.
TK, your perspective, please.
Yeah, and I think, to add a little bit to what Dan said, is a matter of trust, and what Will said is a matter of getting more into the mainstream. One of the things that's probably one of the hardest, most thankless jobs is to get these systems characterized and capable of being production ready in the aerospace world. And I see from looking at the attendee list today, we've got a lot of subsystems manufacturers on the line. And for those that are not engine or not aircraft OEMs, one of the most important things we can do from an additive perspective is get the machines and the materials qualified through MMPDS. And the team, especially at Velo, has been working hard to get these materials characterized, get them into a standard environment where subsystem suppliers, like some of the work I used to do at Honeywell, are part of that action, and they can actually depend on this for production capable parts and getting those into commercial service and into an FAA certified environment. I think from my standpoint, that's the thankless holy grail of this whole thing, is being able to produce these parts in a manner that the FAA will sign off on in a consistent way. And I think we're getting to that point now as we've moved through with Battelle and the team there on MMPDS.
So what makes part selection possible? TK, Daniel, which one of you would like to lead the charge on this one?
I'll let Daniel start.
All right, I'll jump in on this. The major driving criteria is the complexity and cost of manufacturing the part in an alternate method. If I can make something with a 3-axis machine, I mean, that's going to be the way that I go. Additive, where it shines, is in complex geometries. Volutes, airfoils, anything that is going to be either complex to manufacture traditionally or something that I'm going to have to cast, which has a whole lot of other implications, especially in low rate production like I do. So anything that's complex and difficult to manufacture opens the door to having it be an additively manufactured part.
Okay.
Yeah, and to add to what Daniel said on the complexity, I mean, I think we put up one slide here that shows the kind of development that we look for in terms of complex shapes. This being a shrouded impeller. For those of you that are in the turbo machinery business, you're familiar with what a difficult challenge this is to manufacture as a cast part, and try to get all of the air passages perfectly clean and the surface finish the way you need it. And the kinds of things that we look at now in terms of metal additive is being able to print these without the support structure, because that support structure is a lot of cost to put it in, and it's a lot of cost to take it out. And so some of the more advanced technologies that we're looking at enable this kind of shrouded impeller without the use of supports. So when you're looking at relatively difficult 3D manufacturing shapes, like Daniel was mentioning, where you've got airflow, you've got flows that you're trying to control, temperatures you're trying to control, whether it be in a combustor, whether it be an impeller, whether it be in a turbine, airfoil. This is the kind of thing that today is really coming around from a 3D metal manufacturing perspective. I know that when I was first doing additive and prototyping, it was in polymers, and then we were turning that into casting. And now you have the ability to just go direct to a printed output with much better than as cast properties, which is a terrific step forward.
Right. Getting better than cast properties is a huge thing. Like I said, earlier, there's been additional trust in additive. When additive first came on the scene, we sort of knew that the properties were better than cast, but maybe not quite wrought. And in typical engineering conservative design, we would always usually assume cast properties. And as more and more data on the properties of these metal additive parts have come out, we're starting to see the needle shift to where you can assume better than cast properties, and you can get closer to what the things actually have, and then you're going to have a part that actually is better than the cast part. So that's a big leap forward, is to say it's not just a replacement for casting. To be faster, quicker. You don't have to, develop the tooling. It actually is a better part. And then to expand on the on the support structure, which is obviously a big thing. Obviously, shrouded impellers are key in turbo machinery, and the properties that play into that. Obviously, being a rotating part. It's not just straight up strength. It's the circularity of the part. It's any deviations in the surface. It's uniform material properties all around. And when you print at a 45 degree, you can impact some of that. So when we print shrouded impellers, we prefer to keep them flat to the build plate, and you can really only do that with a support free solution.
Yeah, that's a great point, Dan. I mean, when we have axisymmetric parts, impellers, turbines, etc., housings, we always have them basically pointed in the vertical direction. And so that really helps with cylindricity. You don't have this problem of, as the part is cooling down from the printing process, you don't have differences in the cool down and the vertical direction versus the horizontal that causes oblong shapes. I'd say there's, relative to, there was this, Dan, you also brought up the point about the properties. And one thing that's, consistently that we're seeing is that the microstructure in laser powder bed fusion, additive manufacturing is much finer than casting. So casting is I'd say an older process. I mean, I think it's thousands of years old, literally. Not nearly as well controlled, but also it does create much larger grains, which it causes lower strength. So there's a definite advantage, and there's science behind why we're getting much better material properties than castings as well.
All right, I'm going to make sure everybody knows that, so we're not doing the Q&A period necessarily at the end of all of this, that we'll take questions during the middle of this discussion today. So I just want to make sure people know that you can put your questions in there. And so I'm going to ask one, because we do have one that's come through already. And it's, are there material specifications for 3D printed parts? And if there are, does that kind of lock you into a vendor? Who wants to jump on that?
I'm happy to take that, because that's basically my day job at this point in time is all these material specifications. So yes, there are. There's the AMS 7000 series. So AMS is the aerospace specs that the Society of Automotive Engineers authors. So there's a range of those around the powder, the process, and thermal treatment as well. They are not vendor specific. They're in terms of printer specific. They're meant to be general, so you won't pull up there and see necessarily, say, Velo3D's name in there. However, a lot of times these data sets are produced on a certain machines, certain printers. So generally speaking, if you're part of the process, you can find out what printers are used, and that just helps de-risk and look at the variation that you can have from next generation systems such as Velo3D's Sapphire suite of printers versus other systems from, say, 10, 15 years ago. So point being is it doesn't lock you into vendors, but there is still a preference to use the vendor that has the data behind the spec when the spec was generated.
Okay, I'm going to toss one to Daniel right at the moment. I know this is kind of in your wheelhouse. It's your day job, but can you give some more detail on the actual parts selection process?
Yeah. So when we decide to make a part out of additive, it's usually to fit a specific role in the engine. It's usually, I mean, in doing the low rate production, or sorry, the low rate prototype that eventually goes to production type stuff. A lot of it is parts that would be cost prohibitive to cast. If I have a housing or a a support piece or a volute or a crossover or something like that maybe could be built in a traditional cast environment. It could be built as an assembly. When we might be doing 3 test rigs and we have to be done in 6 months. There's no way to cast that part in that kind of time frame. So that's usually what drives us towards additive. It's something that requires rapid turnaround for testing. I don't do a lot of production. I don't do a lot of field type stuff. Most of my stuff is research and development. So I'm taking a design very rapidly to a test rig, to a test engine, to a flow stand or something like that. And, it's the rapid turnaround for any other, method. It sort of seems obvious, but, I'm not going to make a part that I can quickly make on a 3-axis mill in a couple of days on an additive machine. I am going to build something like, I've built combustors like the ones that are shown right here. I've done 3, 4, 5 different designs on combustors within a couple of weeks, and then flow tested them, to each other. That's something I can't do with any other manufacturing method. So I think to answer your question, it's more driven by the purpose than it is the actual part.
Okay, Dan, thank you. We have another audience question, and it is, do we have data comparison on CAS versus 3D based on rainbow tests specifically for turbine airfoils? Will, you want to take a shot?
Sure. So we've seen some customers experience with metal AM that they have higher durability of components when they, this is more in the in static turbine components, so it's not specifically airfoils, but there is improved durability in the field due to the improved material properties in some combustor components. So it's not specifically airfoils. A lot of times with airfoils, those are still, especially in the field, those are single crystal alloys or cast materials such as MARM 247 that are not mainstream yet in laser powder bed fusion. But that's, those kind of materials are certainly on several people's roadmap, but just in terms of back-to-back comparison, it's to answer the question, it's been, yes, there's been an improvement in life, their durability of the component, but it's been more in static components in extreme hot environments.
Okay, thank you. So how about supply chain issues? Does additive manufacturing face any issues in the supply chain? And if so, are they specifically geographic? TK.
Well, I would say, when you look at the whole area of metal additive, and Dan talked a little bit about in the prototype world, I would say really from a supply chain perspective, that's more a question of matching the part design with your technology, and so that's more of a selection process. And at least the manufacturers that are capable of printing it, you'd like to have the printer geographically near you because it just helps with the relationship of getting the part built, actually getting it back to being evaluated. I mean, you don't want to have your design studio in Wichita and your printer in Europe because you'll get it printed in a day and it'll take you 12 days to get back through customs. So that's not going to help you at all. But if you're in Wichita and you have an additive printer that's you're working with in Oklahoma or Texas or any of those areas, it's nice to have that relationship on the same time zone. In terms of production processes, because I'm more focused on getting those prototypes down and in the stream into production. I would say in that case, you can produce it almost anywhere with the machines that Velo is doing, at least, because there's not that much machine to machine variation, and that's really what they've worked on is to reduce that. So where you actually print it is kind of up to you. In that case, if you were actually printing a finished part in production, and you're based in the U.S., but your customer's based in Europe or your customer's based in Asia, and you could actually finish the assembly locally. You could finish it locally, run it through your quality system locally, ship it to your customer locally, and really cut a huge amount of supply chain time. And I think everybody at this point is more focused on time, especially with the number of issues that we're having in transport and customs and moving goods across the world. So I would say to a very large degree, if we get these parts into printed status, you get a lot more flexibility in how your supply chain works. It actually helps you out, as opposed to casting, where you have to go into the casting foundry and you've only got one or two within a geographical location. So from a problematic standpoint, I think the bigger issues are making sure we've got the material characterized, that the material is coming through cleanly, that it's used in a way and printed in a way that gives you the output material characteristics that you want in that finished part. But once you get it ready for production, I think you're pretty much good to go.
Will or Dan, anybody want to take a crack at that?
Yeah, I think there's certainly this aspect of wanting to have a consistent process. And so we've drilled down on the Velo 3D side. We've really developed our system to be, or with the end goal of serial production in mind. So it's a full stack solution of software and hardware to drive stability into the system. Part of what we offer as well at Velo 3D is with our Assure quality software. So this is basically real-time telemetry where we're logging data throughout every single build, and it basically offers this playing field of you know the tool health, so the printer health before the print of your specific part. You then have control charts that are being logged at 1 hertz basically throughout the entire process. So it's extremely, or sorry, I should say one time per second, so 60 hertz. But anyway, it's extreme, high speed data, and you're seeing if there's any issues that happen with the build. And this really helps our customers like Dan to have confidence in the parts that are printed on our systems.
All right, we have another audience question here. Going to toss out to you guys. So you've been talking about that the properties are better than cast. So is there now significant material properties data available to support the standard types of analysis required for fatigue, durability, crack growth, all of that type of stuff?
Yeah, so I'm happy to take that question, actually. So what we're doing, and TK talked about this previously with MMPDS, is we're characterizing the material to the MMPDS Volume 2 requirements. There's certain minimum requirements when submitting data to MMPDS around number of machines, number of lots of powder, or different lots used, number of heat treat cycles, etc. So it's a nice, robust data set. The tensile data and other types of allowables are absolutely required. Then there's others such as fatigue crack growth that are optional. Right now at Velo 3D, we're working closely with key customers to understand what specific allowables they need for Inconel 718, for example, to make sure that as we characterize the material for our next submittal to MMPDS, that we have all the different types of stress required to make this truly a usable material. I mean, already we're not just analyzing room temp data, we're analyzing room temp and high temp data throughout the operating range to make sure that you have the same quality of data set that you have for ROT and Co718 and MMPDS.
Dan, TK?
I think this one's a little bit difficult for me to answer, just because we, as a customer, we've obviously done a lot of internal testing that I can't really speak to. I suspect that there's probably a lot of data out there, that might be program or customer specific, that people have invested in. I don't know of anything public. I think that we've, Kratos has characterized it pretty well, that we feel comfortable with, but I can't speak to that publicly.
This actually brings up a great point, though, where what we've seen is we have a lot of customers and currently and in the past that have simultaneously been running the same bars. I mean, the test houses are getting rich off of all these internal specs because everyone's doing the same test side by side in parallel, and they all consider it proprietary. One of the challenges there is once you generate that data, that's very expensive data, especially things like the decrack growth. And so once a company pays that, they don't want that data to be available to their competitors. So it creates this high barrier of entry for adoption of metal AM, because that erodes the business case having to do material characterization. But then at the same time, it drives this inefficiency industry-wide, and in that, Dan, as well as other customers, are having to reproduce the same tests over and over in parallel. So that's why at Velo3D, we're taking the approach to really do the testing ourselves and the characterization of our materials in order to enable folks like Dan to take the data that we have that's publicly available and just use that, similar to what's done today for ROT and cast equivalents.
Okay.
Yeah, and I think that's really an important point, especially for some of we're getting a lot of questions on material properties and how you get to those material properties. And at least my point of view is that the trick here is to get these into a publicly available and certifiable document like MMPDS. The aircraft OEMs always have their material characterization that they do, as well as the engine manufacturers, and they have a direct tie to the FAA for their material characterization. So they're in a bit of a special league of their own. And I'm talking about like the Pratt & Whitneys and the GEs and the Rolls Royces and the Safrans of the world. But the important part for the subsystem providers is to be able to go to publicly accessible data and not have to recreate all this material characterization each and every time they want to do a part. And so this linkage into MMPDS and the various AMS specs that go with that, I think, is a very important piece of the overall breakthrough to commercialize production parts that are metal printed.
All right, so another question out there from the audience, and that is, how far behind the curve are 3D printed composite parts as compared to metal parts? Because there just doesn't seem to be as much readily available information in aerospace to support non-metallic 3D printing.
I'd say, Dan, do you have any exposure with the composite printed parts? I personally don't have as recent of experience being a metal AM company, but
no, all of my experience has been tailored to the metal additive, the titaniums and Inconels and aluminums and things like that. I have I've seen industry articles on composite stuff, and I've fielded a couple of proposals on composite type printing, but I wouldn't say that my experience allows me to speak intelligently on where it is in the industry. I haven't seen any, at least not in the type of stuff that I do for prototypes.
Guys, it's absolutely okay. You don't have to be able to jump smack on it if it's not in your wheelhouse. No problem at all. So how important is the ability to repeat production on the same machine type with a confirmed design? Dan, I think that probably falls in your wheelhouse.
Yeah, it definitely does. Right now, I'm going to say that from a quality standpoint, it's both important and not. I think we're pretty typical in the industry, in which case every build that we do usually has verification that goes along with it, whether we do tensile bars or microstructure coupons, or hardness testing, or the whole gamut, powder analysis. At this point, we're doing that on most of our builds, and anything that's not for internal dev, it's going to have a lot of quality standpoint, a lot of quality information backing it up, and that's expensive. You got to add that to every build that you do. At some point, we will venture out from that, where you don't have to do quality backup on every part, but right now we are. So every part that we make, usually has some backing to it. So whether you build it on, a printer at a Velo printer at one company, or a Velo printer at another company, or a non-Velo printer at a third company, quality is going to be looked at. Now, from a performance standpoint, it's incredibly important because, like we talked about, the types of parts that we select for additive manufacturing, if it's a flow control device, if it's a vane, if it's a combustor that has holes in it, and we dial in those holes, the consistency of whatever device that you're using to control flow, whether it be small holes or veins or whatever, that consistency is key, because I can't go back and if I'm getting various different results, I can't go back and change that. If I go back and change those results with a more traditional machining operation, like punching in the holes manually, or making an assembly with a flow control device or something like that. I'm trying to speak in general terms. If I do that, then I've negated the purpose of additive, which is for rapid prototyping. So from a performance standpoint, from a flow characteristic standpoint, it's very important to be repetitive build after build.
Okay, Dan, I'm going to throw another one your direction, and that's what's the industry perspective on quality builds and finished parts between different service providers, and how does that impact approaches to a scalable supply chain for production?
What's the industry's perspective? We have obviously, we characterize the supply chain. There's strength and there's weaknesses to different printing types, different printing machines. We've got strengths and weaknesses that are tied to different vendors. Some vendors are running EOS machines and they're good at it, and some vendors are running EOS machines and they're bad at it. Some vendors are running Velo machines and they're great at it. Tying in with the technical guys at Velo across the supply chain of people running the Velo 3D machines has been it's been really excellent. We've really liked that we get more consistent results working with various different vendors that are all running the Velo machines than you would. We get a larger spread with vendors running other machines than we get running Velo machines. Now that being said, our quality requirements, doing what I do. I can only speak to my portion of the industry, but we've got a pretty narrow lane in what we're looking for. Obviously, working any sort of ITAR part, sort of leading edge technology. We're limited to U.S. vendors for the most part. I'm typically not going outside the U.S. except for development work. If I'm working any sort of defense project, it's obviously U.S. vendors. I'm working with vendors that have the backing, the quality backing to be able to assess, like we talked about the quality procedures. The vendors that are working, that have great relationships with test houses to test the coupons, good relationships either doing their heat treat in-house to a quality level that we require at Kratos, or have good relationships with outside vendors that we're familiar with. So I guess to wrap all this up, we have a supply chain that we're comfortable with. We know the entire process pretty well, and we work with our suppliers to deliver parts that meet our quality requirements. And if we start working with a new vendor that might be 90% of the way there or 95% of the way there, we'll work to get them delivering parts of the quality that we're accepting of. I hope that answers your question. If I missed part of it, let me know, and I'll try to go back and expand on it.
I'm sure whoever wrote all of that, if you missed part of it, I'm sure they will let us know. No doubt about it. Sort of a follow-up to that, we'll let anybody jump on who wants to take it, and that's, what about dimensional consistency, machine to machine, or even build to build? Anybody want to discuss how that tends to run?
Yeah, I'd be happy to take that. So when we talk about dimensional accuracy, our spec at Velo3D is plus or minus 0.02 of an inch, or that translates to plus or minus 50 microns. And then there's a laser accuracy component, and then there's this thermal stress component or distortion. So that's plus or minus 0.2%. So and that's important just in terms of if you there's a tremendous consistency. When I came to Velo3D almost 3 years ago from working with other metal AM systems, it was immediately noticeable of the repeatability around the build plate, and also repeatability build to build versus other systems that I'd been working with. And it's important when we start to talk about dimensional accuracy when print on a Velo3D Sapphire. If you have, say, 0.2% shrinkage or print an impeller and it shrinks down, that's common just because you're melting material and then it has to cool down after, so you're going to get some thermal shrinkage. You can scale that file, that CAD file, either in the CAD software or also in our flow software. You're able to put a slight 0.2% correction. And then once you do that correction, the repeatability that you get time after time throughout the build plate or build to build will be within that plus or minus 0.02 of an inch or 50 microns.
All right, and sort of a follow-up to that, Will. So what's the minimum part thickness or wall thickness that you can print?
Yeah, so that varies with the angle. So there's this, it's like this, it's like if you're designing quarter mile time, even if you're designing Formula One cars, for instance, is like how fast is your 0 to 60 or quarter mile time? So what the true answer is in actual everyday practice is that the minimum thickness varies as a function of angle, and also whether it's leak tight or if it's non-leak tight walls. So for instance, an Inconel 718 vertical walls, non-leak tight, that's 150 microns or 0.06 of an inch. And I'd say there's also this aspect. So Velo3D has a non-contact recoder in the Sapphire that's proprietary. And this is very important if you're starting to talk about extremely thin walls. We do not have to worry about orientation relative to the recoder and bending over fins and heat exchangers, etc. And then additionally, there's this aspect where, especially when you get away from 90 degrees, because even if you print a simple heat exchanger, you're not going to be printing just straight up vertical walls. That's why this quarter mile time equivalent of metal AM is not truly a great metric of what you can actually produce in parts. When you start to get away from that 90 degrees, that's where Velo 3D really opens up. We have tremendously sophisticated algorithms in terms of how we're printing all of our geometries. The level of algorithms, I was just blown away when coming to Velo several years ago, and we started printing heat exchangers and seeing the amount of control we had over the laser as we print a heat exchanger and the advanced algorithms versus a previous life. It was like being fast forwarded 5-6 years into the future. And that level of sophistication of laser instructions is what enables our customers to print other parts and really have this freedom to design the part that they need versus having such restrictive constraints over build angles, etc.
All right, that got us down into the weeds quite a bit, so why don't we come out of the weeds a little bit and we'll go a little bit broader here. So, gentlemen, why don't you talk a bit about specific design for additive as opposed to how design is done for subtractive manufacturing? Who would like to take that one first? TK, can I pick on you?
Well, sure. I mean, to a very large degree, having grown up in the engine business, the nice part about additive manufacturing is not just the process that you're using to construct it, but its ability to extend the definition of the part and the envelope that the part sits within. So you can take what used to be 14 or 15 parts, and instead of having to manufacture each one of those subtractively and then put them together into a module, you can actually print those all as a single structure, which is a huge enabler. And I think that we're starting to see that in some of the advanced designs that the teams have been working on that I'm familiar with. They're not FAA certified yet, but they're definitely flying in experimental type applications or in space type applications where these configurations have a large number of parts that would normally be separate parts, all printed as a single entity, and that's a huge enabler in your design for manufacturing, because that can drive out a ton of cost, ton of post processing, all of your post manufacturing that you have to do the assembly simply taken out of the loop. Plus, you can generally lighten up the structure as you go through that design because you're better able to optimize the entire assembly. And I'm not sure if we have a slide of that or not, Will, in the packet, but they've done a number of ones like that. The Sierra turbine is a good example. Remind me, it was 61 parts consolidated into one. Yeah, that's it. Exactly. And if you look at that, and if you've ever been doing combustor design, especially thin wall combustor design, to be able to do that is a huge breakthrough in cost and in weight and hopefully in durability as they test their way through this.
Yeah, one interesting tack onto that is, this is a very small microturbine, but also TK, if you can imagine, if you have the 600 millimeter diameter build plate for combustors, that's going to open up a whole other level of parts that can be printed on like small commercial. Can you talk a little bit as well about how you expect that to impact the industry once you can start printing combustors?
Oh, sure. I think, today, if you dial it back into the 1980s, right, we had machined combustors or fabricated combustors. So you take a piece of sheet metal and you'd wrap it and you'd weld it and then you'd start to drill it. So truly subtractive manufacturing. In the 90s and the early 2000s, we more and more went to cast combustor shapes with much more smaller cooling holes, and we were either using percussion drilling or we might have been using laser drilling. Again, at least in that case, you were able to get the liner out as a single entity in a cast formation. But if you're able to actually print the entire assembly, not only can you print the internal and external walls together, then you can also create the combustor dome. And if you're really shrewd, I think you can actually get the swirlers embedded into the print, so that when you actually take this thing out, about the only thing you've got to do is put the injectors in, put the manifold on it, and off you go as a freestanding combustor system. And so this particular example probably takes what I would say in kind of the early 2000s, 2005 was probably 30 or 40 different parts that had to be either welded together or screwed together, and generates a single part printed right off the machine itself. And with that additional diameter, you can do a whole variety of jet engine components in this size class.
Will or Dan?
Yeah, to jump in on the whether you're designing for additive manufacturing or not, there's I would say maybe 3 to 5 years ago in additive manufacturing, if somebody was taking a design, they said, well, I want to make this additive, and you had unsupported features, well, what's the go-to solution? We'll tilt it at 45 degrees, and that's that's all well and good until tilting it at 45 degrees causes other issues that you then have to work around. Like we talked about the cylindricity of a part. Maybe you've got airfoils or vanes that are going to build different on one side versus the other. The possibility of the part cracking. So then you start to work backwards from that, and then you start to say, okay, well, I can print it at 45, but then I've got to machine it, and I've got to add extra steps or whatever. When you don't necessarily have to put as many supports in, it allows you to instead of trying to get your design through, but also fighting additive manufacturing, it allows you to go straight to the design of the part that you want to be at. So that's sort of the major function. I don't have to every unsupported surface that I look at, and this is not a magic bullet. You can't print a perfect disc unsupported, the entire way across. You have to. There are some limitations, but anywhere where I have a cavity, anywhere where I have any sort of roof structure, it's a heck of a lot easier to get that design to build properly in a supportless environment than if I do actually have to put supports in, especially in a way that it's so easy to look at. This combustor is a great example. It's so easy to imagine getting the supports out when you see a cross section of it, but when you actually hold it in your hands and it's a full round thing that you can't get in there to get the supports out, it becomes a lot more real that you see the value of not having supports in there. And then the easy one across the plate is anytime you've got a flange, anytime you've got a roof structure or something like that, and you can put something, you can put a ramp at it at 45 degrees, but that's all well and good. You just added weight there. And adding weight's no good. We don't want to do that. So that's that's an easy minor thing, but it adds up. And not having ramp angles to your flanges it's not unnoticed when you don't have to do that.
One other aspect to that too is.
Go ahead.
All I was going to chime in there was, having lived life in preliminary design for jet engines, engine length is a big deal. So when you can print something at 10 degrees in a cross section, if you're printing sumps, bearing housings, bearing supports, etc., that's a big deal if you can shorten your engine length, because that really helps improve the overall performance of the engine. So. We've seen that with working with a number of customers where we can help them keep things compact versus having to tilt everything at all their interior surfaces at 45 degrees. So, sorry, TK.
But, no worries. I was going to add to what Dan has said, because I think what people forget, and it doesn't matter if you're doing a combustor design or you're doing pneumatic valve design, that most of your surfaces, your interior surfaces especially, you want to have an aerodynamic component to them. You want to keep the shape that you can design in and not have to try to machine it in. And I think the one big part of additive that these systems can unlock is the ability to give that aerodynamic shaping internally with basically no cost. If you really look at these things, I think we all forget that, we talk about sort of the big parts and the airfoils and things like that, but just about everything, even in your secondary flow systems, you'd like to have it aerodynamic because that air is expensive, and the better utilized it is across the engine, the more efficient the entire engine cycle is. Same is true in aircraft components. Most of these aircraft components, you want to, if they're moving air or they're moving hydraulics or they're moving fluids, you want these things to be as aerodynamic as possible or hydrodynamic as possible to make sure you're optimizing those internal performance parameters, because that's always been the holy grail, right? When you can get the mechanical engineer and the aerodynamic engineer to agree that that's the design, and if you can actually manufacture it, you can make a ton of money.
Yeah, there's an interesting aspect to that too. I mean, right here we're showing with a ramjet with those internal passages, but when you talk about things being not necessarily aerodynamic, if you look at conventional heat exchangers, those are truly designed with the manufacturing process in mind of extruded and bent shapes. And when you start to look at the additive heat exchangers, you see much more aerodynamic looking interior surfaces of heat exchangers. As well.
Oh yeah, and you talk about heat exchangers. I mean, those things are brazed, they're welded, they're a nightmare for production. But if you can print the entire surface in the entire heat exchanger as a single unit, I mean, it's an amazing breakthrough in design for manufacturing.
So another question: Velo 3D design, is it faster than other options? And Dan, I think you probably have some experience on this.
Yeah, I would definitely say that it is faster. I can look at a part and I can say, is this going to be a good fit for a Velo machine? Is this going to be a good fit for an EOS or a concept laser or whatever it may be? I can tell you that I can get a lot of parts through without having to tweak roof structures, slant supports, slant roofs, thicken things. I can intuitively say I can get a part to the point where it can be manufactured quicker with the Velo system. It's interesting depending on where in the industry that you are. When we say like, we can make changes to this, to get this thing to print, making a design change might be as easy as going back and changing your solid model and then going back out and print it. Sometimes making your design change requires a reanalysis of the flow. It might require reanalysis from structures. You make a couple of changes and you might be changing adjacent parts. So making a quick part can be incredibly expensive, both in time and man hours to support that. So even simple changes can really add up to cost savings. I will say, again, it's not magic. You can't take the most oddball shape ever and just hit the go button and the part pops out on the other side. Then you go put it in an engine. Everybody knows we're not there yet. But I can get a design that will print on a Velo much easier than a traditional additive manufacturing machine.
Okay, Will.
Yeah, one thing to bring on there, just to add on with what Dan said. So Velo 3D is unique in that if you're in the preliminary stages of a design, when you're still on a 2D basis, you're not even at 3D yet, we're happy to engage you and your design teams free of charge to help provide that design input for your next generation designs to help reduce that amount of iteration that you have to do. Because if you have the part already, the earlier you can involve us in the process, the more we can give guidance and prevent rework. And then the other aspect is once you do have that final CAD file, our flow software pulls in the CAD file directly, so there's no export to STLs, et cetera. So it really helps. Once you have that finalized design, we've worked for several years to really make our user interface seamless in order to be able to allow engineers to really take the design from the mechanical design engineers, manufacturing engineer can pull that directly into flow, and then on the backside just print it.
All right, we have about 4 minutes left, so I'm going to throw this question to Will. It's directed, specifically to Velo 3D, and that is, how consistent is Velo 3D output?
Yeah, so the Velo 3D output, let me pull this up here. So we have over 900 different sensors basically on the Sapphire that's being continuously logged throughout the print. And all of this is logged onto the server. And then we have the Assure quality software, which is basically a dashboard that post-processes and takes that data and makes it in a format that's usable for whether it's technicians, manufacturing engineers, et cetera. And one of the key things here is that it's usable data. It's not just us saying, hey, we're pulling a terabyte of data a week off of the printer, and here you go, have at it, hire some PhDs and let them dive into the data. This is what's driven Assure is these are what our internal process engineers have found as being useful metrics in order to evaluate the quality of builds. So, and this is available for every single print. So we use this, and we're continuing to expand upon it, Assure, with additional defect detection algorithms, et cetera, as we learn more and as we progress. But this is really having this level of data, to my knowledge, is not available with any other printer manufacturer out there today. And so it really drives this consistency across the supply chain. We also feel free to contact me or Velo 3D afterwards as well. We have data as well for tensile bars. Generally, dimensional is quite easy to hit, but we also have material data over several machines over several months that shows the consistency that we're providing in material properties as well.
All right. Dan or TK, any response on that whatsoever? We've got about 2 minutes.
Difficult for me to speak on the repeatability of it because, being in prototyping, we don't make a huge quantity of a lot of parts. But that's growing. So, it's really difficult for me to speak about our development work, but the more parts that we've started to make, I guess I'm going to say that I have seen more consistency with the Velo process, but we're still at a point where we're pretty much inspecting, every part to see the variability of it. And we sort of, as engineers, we know the envelope that we're working in. So it's not, there's, like Will said, there's a couple of percentage, depending on the size of the part. Not every part is the same. Not every part is the same size. The variability is going to depend on the size of the part and the geometry. So you sort of have some intuitive experience with it. That being said, I've seen across the board better improvement in repeatability. I would say it edges towards the Velo that you get a little bit better repeatability on that.
Okay.
Yeah,
Dan,
my
thank
view,
you.
I think from an industry perspective, to close that out, is that, the repeatability will be trust but verify for quite a while. We will always be this way. All the engineers have to have it proven to them on each part until they get comfortable. And you don't know if that's going to be 15 parts, 30 parts, 500 parts, or 1,000 parts. But, initially you've got to be somewhat skeptical about this because you want to make sure that it's done right. And once you see the repeatability come through, then you start to really gain a lot more confidence. And that confidence is based in fact and measurements, not just in heuristics. So I think that's the way the industry is probably going to go on this one.
Okay. It's always interesting to hear a Ronald Reagan quote in an additive manufacturing discussion. Funny how that works, isn't it? So, yeah. Ladies and gentlemen, if we were not able to get to your question today, and we had quite a few questions, I know that a lot of them got answered, but not all of them. We'll make sure to share them with our speakers so they'll be able to respond to you offline about that. Before we sign off, I'd like to thank our presenters, Daniel, TK, and Will, as well as our sponsor, Velo3D. And within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to share that with your colleagues and peers who may not have been able to listen in live today, and they'll be able to check this out on demand. Thank you so much for attending, and have a wonderful remainder of your day.
Thanks, Ed. Thanks, everyone. Real pleasure.
See you later.